In this lesson, we're going to look at how to take a real-world problem and analyze it, come up with an equation in part one, and in part two, we're going to look at how to graph it. So this is the jeweler problem. We have a jeweler that makes really high-end gold and diamond necklaces and rings. The rings require 5 units of gold and 5 diamonds. The necklaces require 15 units of gold and 3 diamonds. The jeweler has 1,200 units of gold available, 720 diamonds, sells the rings for $20,000 and the necklaces is $40,000. How many of each should she make to earn as much money as possible? So let's just kind of approach this from a trial and error standpoint. One strategy would be to make all rings. Since the rings require 5 gold and 5 diamonds, we could figure out that 1,200 gold can make 1,200 divided by 5, which is 240 rings. The diamonds, 720 divided by 5 diamonds per ring, is 144 rings. So we're going to run out of diamonds at 144, which is a long time before we run out of gold. We have enough gold for 240, but not enough diamonds. So we can make 144 rings times $20,000 is 2.88 million, which is not bad. Another strategy would be to make all necklaces. Since the necklaces need 15 gold and 3 diamonds, we have different numbers that we can make. We have enough gold to make 1,200 divided by 15 gold per necklace is only 80 necklaces. But the diamonds, since we only need 3 diamonds per necklace, we can do 720 divided by 3, which is 240 necklaces. Now, we have enough diamonds for 240 necklaces. We don't have enough gold. We're going to run out of gold first and only be able to make 80 necklaces. But 80 times 40,000 is 3.2 million, which is better. But what about some sort of mixed strategy where we do a little bit of each? We could, let's just take a guess, let's make 100 rings, which uses 500 gold and 500 diamonds because every ring needs 5 gold and 5 diamonds. So if we subtract from what we've got, we've only got 700 gold left, and then 720 diamonds minus the 500 we've used, we've got 220 diamonds left. Let's see how many necklaces we can make with those. We take the 700 gold we've got, divided by 15, because that's how much gold is in a necklace. That gives us 46. It's not exactly 46. There's a decimal there, but we don't have enough gold to go to the next number, 47. So we have to round down in this case. Same thing with diamonds. 220 diamonds divided by 3 diamonds per necklace gives us 73 with a decimal, but we've had to round down because you can't make a necklace that only has fewer diamonds. So we're going to run out of gold first. We can make 46 necklaces. We figure out the total money. 100 rings times 20,000, 46 necklaces times 40,000. Put it all together is 3.84 million, which is better than all rings or all necklaces. But we just kind of guessed that 400 rings was where we wanted to start. And who says that's the right amount? So let's take a look at how we can analyze this and figure out exactly what the best strategy is. These are things that are constants in this problem. The amount of gold in every ring, the amount of gold in the necklaces, the diamonds in the rings, the number of diamonds in the necklaces, how much gold we have available, how many diamonds we have available. Those numbers we know. They're in the problem. We can't change them. They're what we call in math a constant. But there are also some variables. These are the numbers of things that do change, that we do have choices on. The number of rings that we make, the number of necklaces we make. Those are not the same in every situation, and so as variables, we can, well, give them what we use, just a letter. Let's use X for rings, Y for necklaces. Now, going back and looking at the problem, we can come up with some equations. For example, if 1 ring is 5 gold and 2 rings is 10 gold, 3 rings is 15 gold, every ring is another 5 gold. So the amount of gold that we use total is going to be 5 times the number of rings. Since the number of rings is a variable, which we've decided to call x, the amount of gold we use in the rings is 5x. Let's look at the gold for the necklaces. Now there's 15 gold in every necklace, so it's going up by 15 every time, and the amount of gold in every necklace is 15 times the number of necklaces. Since the number of necklaces is a variable, which we've decided to call y, the amount of gold in the necklaces is 15y. We can do this with diamonds too. Since the diamonds are 5 diamonds per ring, it's going to be 5 times the number of rings, and that's x, which is one of our variables. We get 5x. We can do this with necklaces too. Every necklace requires 3 diamonds. So 1 is 3, 2 is 6, 3 necklaces is 9, so it's 3 times the number of necklaces, which is 3y. Now, we put those together to make the totals. The amount of gold we use up in the rings and the amount of gold we use up in the necklaces has to equal the total amount of gold we have available if we want to use it all, which, to make as much money as possible, we do. So we've got 5x is how much gold are in our rings, 15y, how much gold was in the necklaces. Add those together, that has to equal 1200 because that's how much gold we have. Same thing with the diamonds. 5x is the number of diamonds in the rings, 3y is the number of diamonds in the necklaces. Add those together, it has to equal the total number of diamonds, which is 720. So that is how we write the equation from the problem. When you do the farmer problem, I'd like you to use X for the acres of corn, Y for the acres of soybeans, and you're going to need 3 equations. One for fertilizer, one for pesticide, and one for just the total number of acres available. In the bakery problem, our choices are making bread or making cookies. So those are our variables. You're going to need to write an equation, one for flour, one for sugar, and one for the amount of time in the ovens. Finally, for the toy maker problem, let X be the number of cars, Y be the number of toy airplanes, and the 3 equations are going to be one for plastic, one for metal, one for the amount of time in the machines. In part 2, we will look at how to take those equations and graph them.